This is Lecture 4, Predicate Logic Part 1. Okay, so today we're going to talk about predicates, variables, and quantifiers, and we're going to look at translations, equivalences, and negations in predicate logic. So until now, we've been studying propositional logic. However, there are cases in which it's just not going to be enough. Let's look at the following example. This says, well, premise 1, all men are mortal. Premise 2, Socrates is a man. Does this follow, then, that Socrates is mortal by propositional logic? Not really, right? Because this is going to be P, this is just a separate statement Q, and this is an entirely separate statement R, right? This first statement has nothing to do with Socrates. This second statement has nothing to do with mortals. How are we going to connect one with the other? So even if we tried restructuring the first premise as a conditional, right, we'd be looking at something like, if one is a man, then he is mortal, and Socrates is a man. We still run into the same issue, that propositional logic treats a proposition as an indivisible atom. We can't unpack its structure to apply it to Socrates in particular, right? It's kind of blind to the actual qualities or subjects at play here. Okay, so the best that propositional logic could do in this sort of case is if we went ahead and rewrote that first statement as a conditional specifically about Socrates. So if Socrates is a man, then he is mortal, right? Or then Socrates is mortal. So you could then identify your P here. You can identify your Q here. So if you have if P then Q, and you have that antecedent P, then you can conclude Q in propositional logic. And what I've done here is actually a proof. It's actually using laws of inference that we haven't studied yet. We're going to get back to those a little later. But this is just to demonstrate that, yes, propositional logic, this is how we can kind of make a deduction. But by doing this, we're losing the power of generality that a statement like all men are mortal has to begin with. Okay, so propositional logic cannot capture that internal structure, the idea that mortality applies to all men, and then also to Socrates specifically. Okay, and now this is where a new system, predicate logic, is going to come in. Okay, so this allows us to represent general statements and apply them in specific cases as well. Okay, so this system is going to have a few new features compared to propositional logic. First off, you've got variables, x, y, and z. This is going to stand for some arbitrary element of a domain. So, for example, if the domain that you're talking about is all people, then x could be you, me, or Socrates, for example, right? So x is just any person, and then we can have a specific instance of that. Then we've got predicates. For example, P and M. These are functions that describe an attribute of that object or element of a domain. Okay, so M might stand for something like is mortal. We can put those variables and predicates together as propositional functions. We'll get P of X or Q of Y and Z, something like this, right? And now propositional functions are going to be expressions that contain variables and a predicate together simultaneously, right? So you might be left with something like M of X, meaning X is mortal. Okay, so let's see how an example of this might work. Let's suppose we'd like to convert the following statement to predicate logic. X is greater than 3. First off, we're going to identify our variable. X, in this case, it's the subject of the statement. Then we've got P. This is our predicate. This is going to be that property, is greater than 3. Okay, so this is a property the subject of the statement can have. Then we put them together, and we're going to create a propositional function. So P of X. In this case, X is greater than 3. Okay, so we've now translated this entire statement in such a way that the subject, x, is actually separable from its property, p, something that was not previously possible in propositional logic. Okay, so this subject could be replaced with a different subject. This predicate could be replaced with a different predicate. Okay, so it's not just one indivisible atom anymore. Now let's think about truth values of propositional functions. Okay, so a propositional function becomes a proposition when the variables are replaced with actual values from a domain. So as it stands, with a variable, its truth value is indeterminate, right? When we say something like x is greater than 3, well, it's going to depend on what x is, right? So let's see how this works. Let's take a different example. Let p of x now mean x is greater than 0. The domain of x being all integers. So whenever we do deal with subjects and variables in predicate logic, we want to also identify a domain. Who are we talking about? What can we select from for our subject? Okay, so I've got 3 simple examples here. P of negative 3, which is saying, well, negative 3 is greater than 0. That's false. P of 0, 0 is greater than 0. That's a statement. That's also false. And the last one is P of 3, 3 is greater than 0. That's true. Okay, so right now, P of x's truth value is depending on whatever we plug into it. Okay, it's true in some cases, false in others. Next, let's look at compound expressions. Connectives from propositional logic still carry over. Okay, so again, if P of x denotes x is greater than 0, let's see how it looks with our connectives. So first we've got the disjunction. P of 3 or P of negative 1. Well, 3 is greater than 0 or negative 1 is greater than 0. The first part is true, the second part is false. For disjunction, that's sufficient to call the entire thing true. We've got the conjunction with the same elements. The first part's true, the second part's false. Both needed to be true in order for the statement to be true, so that's now I get a false value. Conditional, we have a true antecedent, false consequent. That's a false statement. And then we've got the negation. If we put a negation in front of this consequent here, then we've got true, and that is a true statement. Okay, so just to reiterate the point, expressions of the variables are not propositions, and therefore do not have truth values. Okay, so we can look at 2 examples here. Suppose I have P of 3 and P of y. Well, we don't know what y is, so we cannot evaluate its truth value, and therefore this entire conjunction has an indeterminate truth value. The second example, if P of x, then P of y. Again, we don't know what x and y are. We have no idea what their truth values are. Okay. However, when variable expressions are used with something called quantifiers, they become propositions and will have truth values. Okay, we're going to see in a second what these quantifiers are. Okay, so now we're going to see how they allow us to make broad statements that cover domains without us having to check one value at a time. Okay, just like we were doing here with the 3 and 1 and so on and so forth. We can now avoid that process with quantifiers. So what we have is something called the universal and the existential quantifiers. So what are these? All right, so they're written with these symbols. So we've got this upside down looking A for the universal quantifier, this backwards E for what's called the existential quantifier. And these are symbols that indicate how widely a predicate applies within a domain. Okay, so for the universal quantifier, we're going to put this upside down A next to our x. And how we would read this is for all x in the domain. Okay, and then you put a predicate or a propositional function after that. So you've got for all x in the domain, P of x. For all x in the domain, P of x is true. Okay. Same idea with the existential quantifier, but this one means, or kind of reads as, there exists at least one x in the domain, such that it fulfills whatever our propositional function is. Okay, so this is kind of like all, this is some, at least one. Okay, so for some x in the domain, P of x is true. Let's look at an example real quick. So if P of x again means x is greater than 0 and the domain of x is all integers, then with the universal quantifier, so we're going to write universal quantifier on x of P of x, this becomes all integers are greater than 0. And that's obviously a false statement, right? If we put it with the existential quantifier, it's going to mean some integers are greater than 0, and this is a true statement. Okay? So even though we don't have specific values, specific constants, and we're still dealing with variables, we can now evaluate truth values here. Okay? I just want to note that the truth value of the universal quantifier of x on P of x and the existential quantifier on x of P of x depend on both your propositional function and the domain of x. So it's always important to specify what this domain is, because if we said that this was, say, positive integers only or negative integers only, then this is also going to affect our truth values. And another point, the quantifiers are going to have a higher precedence than all other logical operators. And we're going to see how that works out in a second. Okay. So next, we're going to talk about translating from English into predicate logic. So let's return to our earlier example with mortality and Socrates, right? So we had these two statements, all men are mortal. Socrates is a man. We saw how this is going to work with propositional logic and how we'd have to really specify it down to make those propositions identical with Socrates. Now let's see it with predicate logic. So first off, let's define the predicates and the constants. So let's say M is this quality of being a man. So you can say M of x is the same thing as saying x is a man. And U is the variable or the letter we'll use to denote domain. The domain of x is going to be beings, living beings, all living beings, however you want to put it. Okay. X is being pulled from that set. Same thing for T of x. We can say that this is going to stand for x is a mortal, and again the domain of x is beings. Socrates is now like a specific number in those prior examples. He's going to be a constant within this domain of x. Okay, so now translate each statement. The first one says, all men are mortal. So for this one, we can use the universal quantifier now for all x in this domain if, all right, now we can put this part as a conditional, even though it's not written as in a conditional form, right? There is some implication here. If one is a man, then he is mortal. Okay? So he has this quality. So if you have that first quality, you're going to have that second quality as well. And this is going to hold for all x in this domain. The second sentence is Socrates is a man. So you could just, well, I didn't really use a letter here. I could have used something like that. But we can also just put in the entire word Socrates. M of Socrates just means Socrates is a man. Same thing for our third statement. Socrates is immortal. T of Socrates. Okay? So we're going to come back to this example when we talk about inferences and proofs later on to show how we can actually arrive at a conclusion using predicate logic and using these statements that we've now translated to. All right, let's look at two more examples next for for translations. So example B is saying, translate, some student in this class has visited Canada. Okay, so let U, the domain of X, be all people. We'll use C of X as a propositional function for X has visited Canada. And we'll use S of X to mean X is a student in this class. Okay. Now we're dealing with sum here, so we're going to want to use the existential quantifier. All right. So we can put it together like this. We've got the existential quantifier on the outside. This parentheses is to show that this is applying to the entire conjunction. And what we're saying is that there's some X which meets both of these criteria. So S of X and C of X. In other words, there exists someone who is a student in this class and has visited Canada. Okay. Now, how about example C? Translate, every student in this class has visited Canada or Mexico. We can use the same propositional function from before for Canada. M of X here can mean X has visited Mexico. S of X again can mean X is a student in this class. Now let's think about this. Which of the following choices do you think is correct? And here they are. So A has the now universal quantifier, right? Because we're talking about every student. So we've got the universal quantifier outside. And then inside these brackets, we've got this person is a student, and they've visited Canada or Mexico. Choice B, we've got the universal quantifier. And now, instead of a conjunction, we've got a conditional. So we're saying that if this person is a student in the class, then they've visited Canada or Mexico. So take a moment to think about which one of these choices makes more sense. Okay. Of the two of them, actually, B is correct. Choice A here is translating to everyone, right? This is true for all people. For all people, they are both students in this class and have visited Canada or Mexico. Okay, that's not true. So B, on the other hand, is translating to for all people, if they are a student, then they have visited Canada or Mexico, right? So they need to fulfill this criteria first before we can say that this is implied or this follows from it. Okay, so you want to be careful about, especially when we're using the universal quantifier, which one of these symbols we're going to put in here. Next, we're going to talk real quick about equivalences. So predicate logic statements are equivalent if and only if they have the same truth value for, number one, every predicate applied to these statements, and number two, every domain used for the variables in the expressions. Okay? And we're going to see more about how this kind of plays out and what these two rules are going to mean. But for now, we just have some quick equivalences where we can rewrite these quantifiers as either conjunctions or disjunctions. Okay? So the universal quantifier, this would mean for all x in our domain U, P of x is true. This is the same thing as saying, well, P of 1 is true, and P of 2 is true, and P of 3 is true, where 1, 2, and 3 here just stand-ins for specific instances of your subjects. If x, is talking about numbers and things like that, or we're in the domain of integers, then these could actually just be literal numbers. If we're talking about people, these could be names, something like that, right? Instead of 1, 2s, and 3s. So the universal quantifier is just saying that, well, it's this one, and the second one, and the third one, and so on, for everything in the domain. The existential quantifier, on the other hand, is operating on disjunctions here. Okay, so for at least one x in the domain U, p of x is true, this is the same thing as saying, well, it's either true for p of 1, or true for p of 2, or true of p of 3, and so on and so forth. And again, it's inclusive, so it doesn't just have to be one of them. It could be some combination of them. It could even be all of them. Okay, but it's not specified here. Okay, so if we just say for at least one. And then the final thing we're going to talk about in this video is negating quantified expressions. So let's look at the following example. So suppose we've got this propositional function j of x, and it means x has learned Java. Our domain U here is just going to be students in your class. Okay, so for all x, j of x is going to translate to every student in your class, that's your entire domain, has learned Java. Now what happens if we put a negation in front of that whole thing? Okay, this is going to mean it is not the case that every student in your class has learned Java. Okay, in other words, some students have not learned Java. Now this second statement is making use of this word some, which means we could actually apply the existential quantifier here. We could rewrite that as for some x in our domain, the negation of j of x, right? Some students have not learned Java. And this is going to bring us to our first De Morgan's law for predicate logic. So if you remember, De Morgan's law from last time was talking about negation of a conjunction and negation of a disjunction, how we can kind of distribute that and flip the values of the disjunctions and conjunctions, right? We can swap from one to the other. Same sort of thing is kind of happening here. We're taking this negation, we're putting it within the quantifier. And by doing that, the quantifier is changing, and the negation is applying directly to your propositional function. Okay, so in general, this law is the negation of the universal quantifier of p of x is equivalent to the existential quantifier of the negation of p of x. Okay. Similarly, let's say we started off with the existential function, right? So the existential quantifier of j of x. There exists at least one student in your class who has learned Java. Now, if we put a negation in front of that, it is not the case that there exists at least one student in your class who has learned Java. So there's not even one student in your class who has learned Java. In other words, none. That one we can rewrite as for all x, not j is true, or the negation of j is true. Okay, so our second law is going to be the negation of the existential quantifier of p of x is equivalent to the universal quantifier on the negation of p of x. All right, so these were our De Morgan's laws, and this is our introduction to predicate logic. We're going to pick up from here next time. If you found this lecture helpful, please give it a like and subscribe so you don't miss the next one. Thank you for watching.